Hello, let's start with the next section, dimensionality reduction with principal component analysis. In this section, we'll discuss a technique for reducing the dimensions of data called principal component analysis, PCA. We'll use PCA to visualize a high-dimensional dataset in 2 dimensions and to build a face recognition system. Now we move on to the first video of this section that deals with principal component analysis. In this video, we're going to learn what PCA is, and then look at variance and covariance metrics. We'll also work with eigenvalues and vectors. We'll verify our calculations of both using numpy. Problems involving high-dimensional data can be affected by the curse of dimensionality. As the number of dimensions of a dataset increases, the number of samples required for an estimator to generalize increases exponentially. Acquiring such large data may be infeasible in some applications, and learning from large datasets requires more memory and processing power. Furthermore, the sparseness of data often increases with its dimensions. It can become more difficult to detect similar instances in a high-dimensional space, as all instances are similarly sparse. PCA, also known as the Carhoonan-Loève transform, KLT, is a technique for finding patterns in high-dimensional data. PCA is commonly used to explore and visualize high-dimensional datasets. It can also be used to compress data and to process data before it's used by another estimator. PCA reduces a set of possible correlated high-dimensional variables to a lower-dimensional set of linearly uncorrelated synthetic variables called principal components. The lower-dimensional data preserves as much of the variance of the original data as possible. PCA reduces the dimensions of a dataset by projecting the data onto a lower-dimensional subspace. In general, an m-dimensional dataset can be reduced by projecting onto an n-dimensional subspace, where n is less than m. More formally, PCA can be used to find a set of vectors that span a subspace that minimizes the sum of the squared errors of the projected data. This projection will retain the greatest proportion of the original dataset's variance. Now let's look at variance, covariance, and covariance matrices. Variance is calculated as the average of the squared differences of the values and the mean of the values as shown in this equation. Covariance is a measure of how much 2 variables change together. It's a measure of the strength of the correlation between 2 sets of variables. If the covariance of 2 variables is 0, the variables are uncorrelated. The covariance of 2 variables is calculated using this equation. If the covariance is non-zero, the sign indicates whether the variables are positively or negatively correlated. When 2 variables are positively correlated, one increases as the other increases. One variable decreases relative to its mean as the other variable increases relative to its mean, when variables are negatively correlated. A covariance matrix describes the covariances between each pair of dimensions in a dataset. The element I, j, indicates the covariance of the ith and jth dimensions of the data. For example, a covariance matrix for a set of 3-dimensional data is given by the following matrix. Let's calculate the covariance matrix for this dataset. The means of the variables are 2.125, 0.075, and minus 1.275. We can then calculate the covariances of each pair of variables to produce this covariance matrix. We can verify our calculations using numpy. This is the code that's used. You can see the covariance matrix here. Let's move on to eigenvectors and eigenvalues. Recall that a vector is described by a direction and a magnitude or length. An eigenvector of a matrix is a non-zero vector that satisfies this equation. Here is an eigenvector. A is a square matrix and lambda is a scalar called an eigenvalue. The direction of an eigenvector remains the same after it's been transformed by A, only its magnitude changes, as indicated by the eigenvalue. That is, multiplying a matrix by one of its eigenvectors is equal to scaling the eigenvector. Eigenvectors and eigenvalues can only be derived from square matrices, and not all square matrices have eigenvectors or eigenvalues. If a matrix does have eigenvectors and eigenvalues, it will have a pair for each of its dimensions. The principal components of a matrix are the eigenvectors of its covariance matrix, ordered by their corresponding eigenvalues. The eigenvector with the greatest eigenvalue is the first principal component. The second principal component is the eigenvector with the second greatest eigenvalue, and so on. Let's calculate the eigenvectors and eigenvalues of this matrix. Recall that the product of A and any eigenvalue of A must be equal to the eigenvector multiplied by its eigenvalue. We'll begin by finding the eigenvalues, which we can use using this characteristic equation. The characteristic equation states that the determinant of the matrix, that is, the difference between the data matrix and the product of your density matrix and an eigenvalue, is 0. Substituting our values for A produces these results. We can then substitute in our first eigenvalue to solve for the eigenvectors. The preceding steps can be rewritten as a system of equations. Any non-zero vector that satisfies the preceding equations can be used as the eigenvector. PCA requires unit eigenvectors or eigenvectors that have length equal to 1. We can normalize an eigenvector by dividing it by its norm, which is given by this equation. The norm of our vector is equal to the square root of 2. This produces a unit eigenvector. We can verify that our solutions for the eigenvectors are correct using numpy. This is the script. The eig function returns a tuple of the eigenvalues and the eigenvectors. Run it, and you can see the eigenvalues and vectors here. In this video, we learned about how PCA works.